Hey guys, today we're going to be learning how to write half reactions of redox reactions. In order to be able to do this, you have to make sure you remember back a couple of videos to how we assigned oxidation numbers. So we're going to use those skills today in writing and balancing these half reactions. So let's go ahead and get started. So let's start with a quick reminder. Oxidation and reduction are chemical processes that occur when electrons are gained or lost. Oxidation is the loss of electrons, like oil, O-I-L, and reduction is the gain of electrons, Rig. So you can think of it as oil rig. You can also think of it as Leo says Ger. Leo, loss of electrons, is oxidation. Ger, gain of electrons, is reduction. Of course, you could also think of it as Ole. But if you do Ole, it's oxidation is loss of electrons, and you have to do the hand movement. It's just the rule. So when we write half reactions, what we're doing is we're taking the oxidation process and the reduction process and separating them out into two separate reaction forms. Now, it's critical to understand that without oxidation, reduction can't happen, and without reduction, oxidation can't happen. So even though we might only show one half reaction or the other, the reality is both are always going to happen together. So this is a technique that we use to identify each half the reaction, and then in the end we're going to go back and recombine them later, and we're going to talk about that when we go into balancing with the half reaction technique. All right, so let's jump right into a practice problem. Here I've got a reaction between elemental zinc and copper ions, creating copper in its elemental form and zinc ions. This reaction is going to involve the transfer of electrons, but how do we know? Well, we need to assign oxidation numbers. Zinc's oxidation number here in its elemental form is 0. Copper in its ionic form is charge of 2+, therefore its oxidation number is also +2. Copper here, elemental form, oxidation number is 0. And zinc here, oxidation number equals the charge, +2. So we see here that the zinc went from 0 to +2, and the copper went from +2 to 0. That means electrons have moved. Well, let's figure out how. Zinc became more positive. That means it lost electrons. Therefore, it was oxidized. So what we're going to do is we're going to write an oxidation half reaction now, and we're going to include the zinc and anything that the zinc contains, or that contains the zinc. So that's going to be your oxidation half reaction. The reduction half reaction, we do the exact same thing, but now we're dealing with the copper instead. So we're going to write the reduction half reaction now. Now you can see these half reactions are fairly simple and straightforward, but in some cases they're not going to be. In some cases they're going to involve far more than just the ions. So when we get to it, we're going to start learning how to balance half reactions, but we're not going to get there quite yet. But just be aware of the fact that right now these are not balanced half reactions. We're balanced maybe for atoms, but certainly not for charge, and in other cases there are other things that also might be imbalanced when simply writing half reactions. In the next video, like I said, we're going to learn how to balance these half reactions out. All right, here's a problem that I want you to try on your own. Pause the video, take a few seconds to work through it. If you get an answer or get stuck, go ahead and unpause the video and we'll work through it together. All right, now that you've had a few seconds to work on it, let's go through it together. Again, the first step is always assigning oxidation numbers. This is another one, looks like the one we just did, which essentially the oxidation numbers are fairly straightforward for you. Ions have the same oxidation number as their charge, and elemental forms the oxidation number is 0. So we know the iron 3+ has an oxidation state of +3. Zinc is going to be 0. Iron 2+ oxidation state of +2. And zinc 2+ oxidation state of +2 as well. We can look and see which one's been oxidized and been reduced. The iron went from 3+ to 2+. That means it became slightly more negative or less positive. That means it must have gained electron or electrons. Zinc went from 0 to 2+. That means it became more positive or less negative. Therefore, it has been oxidized, lost electrons. So we're going to write the oxidation half reaction first, which is involving the zinc. Remember, we always write not just the zinc, but anything that is containing the zinc as well. In this case, it just happens to be the zinc. And in the case of the reduction half reaction, this will be iron. Now you'll notice I dropped the coefficients with the half reaction. You actually don't need to do that. Normally you're going to be given this unbalanced, all right, and the reality is these would theoretically cancel because you need to have it in the most reduced form. So in the end, the half reaction here is going to be inherently unbalanced to begin with. And so until we start learning how to balance half reactions, you don't really have to worry about carrying down the coefficients. I just did it here to show you kind of what we're doing in terms of how we write our half reactions. But again, this will be more focused on in our next video about balancing half reactions. So let's take a step through this next problem. In this next problem, we've got copper reacting with silver nitrate, producing copper nitrate and silver solid. Writing our half reactions requires us to first write the oxidation numbers of each element. So let's go ahead and write the oxidation numbers of each element. Copper here is 0. Silver +1. Nitrate as a whole is -1. Therefore, the oxygen is going to be -2 each. Times 3, that's -6. Nitrogen in this case has to be +5 in order to get us to our charge of -1. Copper in this case is going to be +2 because remember each nitrate's -1, so therefore it's -2 from the nitrate, must be +2 from the copper. Nitrogen again +5, and oxygen still -2, and the silver here in its elemental form is 0. Now you'll notice not everything changed. The nitrogen and the oxygen did not change across the course of the reaction, but the copper was oxidized, and the silver was reduced. So if we write our oxidation half reaction, we're going to have to account for that. So let's go ahead and write our oxidation half reaction. In our oxidation half reaction, we can see that the copper went from copper 0 to copper 2+. That means we're going to write that. In addition, we're going to include that nitrate here. So we're going to write it such as this. Again, when we write our half reactions, we include not just the thing, the element that's being oxidized or reduced, but every compound that that element is in. Same thing goes for the reduction half reaction. Again, we've included the nitrate. That's important. In the end, whether you're writing it such as this, or if you ever happen to see it with someone just writing copper to copper 2+, it really is going to depend on the technique you use. I prefer this technique because in my half reaction balancing method that we're going to talk about in the next chapter, in the next video, you're really going to need all components of every compound in order to do it properly. All right, now this is a more challenging problem. I want you to take a second, try this one on your own. If you get stuck or get an answer, go ahead and unpause the video and we'll work through it together. Now, as simple as this problem seems, it's actually not so simple. Part of the reason it's not so simple is because we have yet to really work with covalent molecules at this point. We are dealing with molecular hydrogen, molecular oxygen, and molecular water. So we talked about how to separate ionic compounds throughout the video, but we really haven't dealt with covalent yet. But we deal with it just the same. Hydrogen here is in its elemental form, oxidation number 0. Oxygen, elemental form, oxidation number 0. On the product side, we have an oxidation number of hydrogen of +1 each, and of oxygen -2. So as you can see, the hydrogen went from 0 to +1, and the oxygen went from 0 to -2. When we write our half reactions, we're going to include this idea. So hydrogen was oxidized, and therefore we're going to write it in our oxidation half reaction. Let's do that first. Remember what I said with ionic compounds. Don't just include the element and any compound where the element is contained. That includes water. So the entire water molecule ends up here. Now that looks like you could not balance it, but in the next video, I'm going to talk to you about how to balance half reactions such as this, even though in the moment it doesn't look like it could be. All right, there is a technique we can use. We're also going to write the reduction half reaction. Beautiful. So the oxidation of this whole reaction is the hydrogen going from H2 into water, H2O, and the oxygen going from O2 into H2O. That's our reduction half reaction. So now we've learned how to write half reactions from an overall redox equation. So that wraps up today's video. Today we learned how to take a redox reaction and separate it into its oxidation and reduction half reactions. Next video, we're going to be talking about how to balance these half reactions and then recombine them into an overall balanced redox equation. I'd like to thank Andy Dew for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.